Okay, as Nancy said, my name is Patrick Hayes. I'm a graduate student at Northwestern University, and I'd just like to thank the organizers for giving me the opportunity to come here and talk about my research. I'm going to change gears a little bit. I think I'm going to come at the question of pharmaceuticals in the environment from a more fundamental level, but I hope my research will be interesting to everybody in the room today. So in the GUIDE group, we've actually published a few papers on specifically antibiotics in the environment and agricultural antibiotics. And what I want to focus on today is oxytetracycline, which is nice because we heard a talk from the Illinois EPA earlier today, and they had a long list of pharmaceuticals they were interested in. Oxytetracycline was one of those antibiotics in their list. So most people are familiar probably with tetracycline antibiotics, but I just want to provide a little bit of background. Tetracyclines are used in both humans and in animals. And it's estimated that around 3 million pounds of tetracycline antibiotics are used for growth stimulation in livestock. And of those 3 million pounds, about 25 to 75% are actually administered, that are administered to the animals are excreted in their active form. So what this means is if you have manure that comes from concentrated animal feeding operations, that manure typically ends in a lagoon. These lagoons are usually lined, but they can leak, and then the leakage can represent actually a really major input of pharmaceuticals, specifically antibiotics, into the environment. What I'm really interested in is this idea of antibiotic resistance, and specifically what is the role that the mobility of the antibiotic in the soil plays in terms of this antibiotic resistance. And Dr. Kelly from Loyola was talking about this just previous to me, this idea that if we have antibiotics in the environment, they can cause antibiotic resistance. And just to kind of show the importance of mobility, I want to give you two simple scenarios. In the first scenario, you have a sticky antibiotic. What this means is the antibiotic absorbs very strongly to the surface of a soil particle, and then the antibiotic is relatively localized, which means if there is a resistance problem or other human health hazard, that's going to be a relatively localized effect. Now, the second scenario is one where you have a very mobile antibiotic. In this case, the antibiotic, when it enters into soils, does not absorb strongly to the soil surface and is really mobile and then moves quickly through the soil. So there's a dilution effect, but at the same time, this means that the threat posed to human health, if there is one, is relatively delocalized. So this gives you an idea of why mobility is so important for understanding the threat posed by antibiotics in terms of antibiotic resistance. And I just wanted to quickly highlight this reference down here that came out in 2007. This actually came out of UIUC and the USDA and also, I think, the Illinois State Geological Survey. And what they found was not only are antibiotics mobile in the environment, but also the genes associated with resistance are mobile in the environment. So you have both of them moving through soils, and they're two coupled problems. And to understand where the genes are going, you have to understand where the antibiotics are going. But at the same time, to understand resistance and the mobility of resistance through soils, you have to look at the genes as well. So if you want to understand pollutant mobility, you really have to understand the polluant's behavior at an interface. So I just have a simple cartoon here to sort of illustrate the importance of interfaces. If you have a pollutant point source, the antibiotics can then leach down into soils where it interacts with the surface of soil particles. And in a process that's really it's just like chromatography to chemists or analytical chemists, where the interaction of this pollutant with the soil particle surface will actually determine how quickly it moves through the soils. And so if you want to study environmental interfaces, there's some really big challenges. First is complexity. Soil is inorganic, it's organic. It's really hard to get a well-defined chemical system to study. The second challenge is separating bulk from surface. So in my case, I'm studying OTC, oxytetracycline, and I want to be able to use a technique that can separate bulk aqueous OTC from OTC that has been bound to the surface of a soil particle. And finally, last challenge is sensitivity. At environmentally relevant concentrations, which are very low, you may have a monolayer or even a submonolayer of antibiotic at the soil surface. And what that means is you have to have a technique that's sensitive enough to detect these low absolute numbers of pollutants. And so the technique I use actually to address all three of these challenges is something called second harmonic generation. So I realize probably most people in the room are not familiar with second harmonic generation, so I just want to provide a really quick qualitative overview of what this technique involves. The second harmonic generation experiment, you take a laser light and you focus it down onto a surface of interest, and then you monitor the second harmonic signal, which oscillates at twice the frequency or half the wavelength. So really the measurable in this case is light. And this process actually has a nice analogy in acoustics. If you have a tuning fork, you hit your tuning fork hard on a desk, and you listen to that tuning fork, you can hear your resonating fundamental. What you also hear, if you listen really carefully, is that first overtone. And that's really a second harmonic signal. We're doing the exact same thing here. We're hitting our surface really hard with laser light, and we're listening really carefully or monitoring very carefully for the second harmonic signal. So why do we use this technique? Well, it's very surface specific, and it has the sensitivity to allow us to watch adsorption in real time. And finally, it also allows us to run experiments under flow conditions. I have a really simple example here of a second harmonic generation experiment. This is actually an experiment on nitrate. Nitrate is not a pharmaceutical or personal care product, but it's actually a common agricultural pollutant. So that's one of the reasons why I'm studying it. You just take a UV-Vis spectrum of nitrate. You see there's an electronic transition about 300 nanometers. If you do the SHG spectrum and you tune across a variety of different SHG wavelengths, you see a flat response. This is just for a fused quartz water interface. But when you introduce nitrate into the system, you see an increase in the SHG signal, which is consistent with the electronic resonance in nitrate. So this is called a resonance enhancement effect in the SHG. And what this means is that we can chemically identify nitrate at the interface and then also probe it spectroscopically. The other important thing to know about SHG is that our measurable, which is the light at the second harmonic frequency, is proportional to the number of adsorbates. So that means as we increase nitrate or OTC at an interface, we're going to see an increase in the SHG signal. So now I'm going to talk about my experimental setup. So I am using a model system. It's much more simplistic than anything anybody else talked about this morning so far. But we have a laser system. We focus it down onto the interface of interest. And then we block our fundamental laser light. But we take our second harmonic light and monitor it using single photon counting techniques. On the bottom half of our setup, we have a Teflon flow cell, and we flow our aqueous solutions through this flow cell, and then we can monitor bulk OTC concentrations using UV-Vis spectroscopy. So if you look at this setup, you see that I have a fused quartz hemisphere here, which is obviously much more simple than the soil particle surface. So being chemists, the way we address this complexity issue is actually using synthetic chemistry to tailor-make fused quartz surfaces that have organic groups bound to the surface of the quartz. And the reason why we use organic groups is because the soil particle is often coated with an organic add layer. And we know from the work of people like Gary Esposito at UC Berkeley that there's actually very common organic structural motifs in natural organic matter. Things like carboxylic acids, phenols, benzoic acids. And you see here we're just using covalent chemistry, carboxylic acids and methyl esters and benzoic acids onto this fused quartz surface. And that kind of builds up towards the complexity of the soil particle. Our other strategy is we're trying to isolate and study individual functional groups and trying to isolate which sort of chemical motifs in organic matter are important for binding OTC. So now that we have our model interfaces in hand, we can go ahead and carry out a second harmonic generation experiment. You see here, this is our SHG spectrum, and we see a peak at about 310 nanometers. And this is actually really interesting because you can compare it against the bulk OTC spectrum, and you see it's vastly different. And that's actually not surprising. When OTC adsorbs to a surface, its electronic structure can be perturbed because of electrostatic interactions or hydrogen bonding interactions, and actually changes the spectrum of OTC at the interface. So then we can sit at 310 nanometers using our laser system and watch OTC adsorption in real time. We start with water. We introduce OTC into our system. We see an increase in our second harmonic signal. This is consistent with OTC adsorbing to the surface of our fused quartz interface. And then we flush the system with water, and we see a decrease back down to baseline levels, which indicates that OTC adsorption is fully reversible. Then we can go ahead, and now that we have an on-off trace, we can carry out the same experiment at a variety of different OTC concentrations and get a binding isotherm. And from this isotherm, this allows us to use the KD model. The KD model is a very simple model that's used to predict the mobility of pollutants in soils. And simplicity is nice because it allows us to take our results and then extrapolate up to soil environments. And also the KD model is used by the EPA, so it's nice. It's a standard technique for predicting pollutant mobilities. So if we just do a unit conversion here on the x and y axis, we can get our KD parameter. And then the KD parameter can be plugged into the equation here for a retardation factor. And you have to use typical values here for the porosity and the density of soil. But what you get at the end is a retardation factor that will be between 1.4 and 2. And just as a point of reference, a retardation factor of 2 would correspond to a 50% reduction in OTC mobility relative to water. So we can carry out the same analysis using all the different model surfaces I talked about earlier. And what you see here is a really interesting dependence on functionality at the surface. You see these benzoic acid groups have very high binding affinity for OTC, whereas the carboxylic acid or the fused quartz surface has a relatively low binding affinity. So this really, one, it tells us something about the importance of organic matter. We see that these conjugated groups are very important, so maybe a pi-pi stacking type interaction might be really important for OTC binding to natural organic matter. The other thing is we have a couple questions that come out of this data. First, why do some surfaces have such high affinity and other surfaces have such low affinity? And the other question is, while these surfaces look very complex from a molecular level, is there any way we can take a result and extrapolate up to more complex systems? And the way I do that is using contact angle measurements. These are contact angle measurements, just a droplet of water on a functionalized surface. The top here is for this methylamide surface. You see it has a lower contact angle. And then for the benzoic acid functionalized surface, it's more hydrophobic, so you see a higher contact angle. We then can convert our contact angles into interfacial energies, and then plot the interfacial energy along the x-axis versus the retardation factor along the y-axis. And we see in a very approximate fashion that the retardation factors increase with interfacial energy. So surfaces that have high interfacial energy or are more hydrophobic also lead to greater retardation of OTC in soil. So this really gets at that first question I was asking, which was, what is the driving force for OTC mobility? It really appears that high interfacial energies will actually slow OTC mobility through soils. And this makes sense because OTC is kind of behaving like a surfactant, comes down to the surface, it interacts with this hydrophobic surface and helps mediate the interaction with water, which makes OTC adsorption more favorable. The second question I asked was, is there any way I can take these systems and extrapolate up to more complex systems? And the way I've done this is by measuring contact angle measurements for different humic acid samples. And you can see by taking the contact angle, we can get a surface energy and then predict a retardation factor. So insofar as my laboratory results mimic conditions in the field, this shows how we can take an SHG experiment, couple it with contact angle measurement, and begin to predict retardation factors for humic acids in soil environments. So with that, I just want to make a connection back to mobility. And that the first connection I want to make is that it appears that benzoic acids will play a really important part in slowing OTC mobility through soils that have natural organic matter. And then also it looks like interfacial energy might be another good predictor for OTC mobility through soils, with surfaces that display high interfacial energy slowing OTC relative to interfaces that show low interfacial energy. And with that, I just want to acknowledge my research group and also these funding organizations. I'll be happy to take any questions.